36 plus minus 0.11 millimeters per year over the last 200,000 years. I have to say that even if we estimated the uplift rate for the upper Quaternary period, I mean for the late Pleistocene period, there are also some indicators which show that this positive movement of the area, the uplift, has continued during the Holocene. You can see here some photos of wave-cut abrasion platforms at the southeastern part of the area, which are uplifted. Of course, we did not date them because we did not find material, but they are recent, very recent, and they are uplifted up to 1 or 2, 1.5 meters above present-day sea level, and we can see here that they are bounded by sea cliffs and in some cases by abandoned notch. And I have to say that this tectonic uplift rate that we estimated gave us the opportunity to correlate the 6 marine terraces which were undated. How we did this? We did the assumption of temporarily constant uplift rate during the late Pleistocene, and we estimated the elevation range of the predicted inner edge, expected inner edge for each MIS sea level high stand. Here in this diagram, you can see with the black thick line the range of the predicted or expected inner edge elevation, and it was compared with the range of the real elevation of the inner edges, which is this thin red line. And we can see here that this gave us the opportunity to correlate the first marine terrace with 5A MIS, the second with the 5C, 5E was already dated, the T4 with the MIS 7A, 7C is already dated, TAF6 with 9A, T7 with 9E, and the last one, T8 with MIS 11C. And here is the final correlation scheme of the marine terraces with the Quaternary MIS sea level high stands. And I have to say that we took into consideration for this case study the sea level curve of Wilbrook et al. 2002. Let's move now to the second case. The second case, as I said you at the introduction, is the southeastern part of Crete Island. Crete Island is the biggest and southernmost island of the Aegean Sea. It is tectonically very active area, since, as you can see here, it is very, very close to the plate boundary. And along the southern coast of the island, there are many, many places where marine terraces, uplifted marine terraces, have been preserved. And there are quite a lot of studies and researches that study marine terraces in order to find out what's going on with the tectonic status in this area, which is really complicated. The area of this case I will present now is has a length of 24 kilometers, and it is east and west of the city of Hierapetra. It is somewhere here. In this area, we estimated, we identified and mapped 5 marine terraces. You can see the map here. They were mapped. They were dated using uranium-thorium disequilibrium dating method. And we correlated these 5 marine terraces with MIS sea level high stand. The lowermost marine terrace corresponds to MIS 5A. And the highest and oldest corresponds to MIS 11C. You can see here that these marine terraces have been offset by the activity of the normal fault of Hierapetra. It is this tectonic line marked here with a thick red line, but I will tell you about this later. Here are some photos of the area. Here you can see that the extensive surface of the marine terrace, which corresponds to 5E, it's the green one. These photos, the first 2 photos, are taken from this area, west of the city of Hierapetra. This photo is from the from the lowest marine terrace, from the surface of the lowest marine terrace, which corresponds to 5A. And this marine terrace is found only at the eastern part of the area. It is not found at the western part of the area, probably due to the activity of the fault. And here is another series of bedrock marine terraces, which are, the photo is from the eastern part also of the area, and I see that they are a bit tilted here. I said about the normal fault of Hierapetra. As I said before, the marine terraces have been offset by this, by the activity of this normal fault. Normal fault of Hierapetra is an important structure for the island. As you can see here, it crosses all the island. It extends into the water both north and south of Crete, and it can be separated into three segments. The two northernmost segments, the northernmost and the middle segment, are present intense morphotectonic characteristics. Here are two photos which show the fault plane. The photos are indicative of a really active, a really very active, recently active structure, tectonic structure. And as you can see here, it is a wine glass valley, which is the result of incision of the Ha River, and it is indicative of the recent activity of the fault. And I have to say also that this photo, which shows a close-up of the gorge, you can see a light-colored band at the base of the fault plane, which is the activation of the fault during the period of Holocene. The height of this band is about 1 meter, and if we assume that this is the Holocene activation of this corresponds to the Holocene activation of the fault, we can conclude a mean uplift rate of 0.1 millimeter per year. I have to say that the southernmost segment of the fault seems to be not that active. I mean, it has not very intense morphotectonic characteristics as the other segments, probably because it crosses easily erodible geological formations, so the fault plane cannot be preserved. And the fault is buried under the alluvial deposits of the Hierapetra plain. But its activity is evident by the presence of uplifted uplifted beach rock just east of the city of Hierapetra at the footwall of the fault. So this is an evidence of the tectonic activity of this segment also of the Hierapetra fault. Here is the concept that we followed to estimate the vertical displacement due to the activity of the fault. In this figure, the first part shows the sequence of marine terraces before they are displaced by the fault, and the other figure shows the displacement due to the activity of the fault over the last 400,000 years. The concept was that we tried to estimate in detail the elevation of the inner edge of each marine terrace on both sides of the fault, at the footwall and at the hanging wall. And the difference of these elevations allowed us to estimate the rates of tectonic uplift due to vertical displacement due to the activity of the fault for the period between the formation of two marine terraces. And let me show you in detail what we did. Here is a map which shows the sites where we measured in detail the elevation of the inner edges. 143 sites, which are represented here by black dots, and we projected the elevation of the inner edges at these sites with the vertical distance of each site from the trace fault, from the trace of the fault. And we produced this diagram, which shows the deformation of the paleo shorelines. Here, as we can see, there is an increase of the inner edges of the marine terraces, at least for the four of the marine terraces of the paleo shorelines from east to west, and the general geometry of the paleo shorelines is indicative of a normal fault. You can see here also that we have we performed sections, topographic sections, In 4 places, 2 were at the hanging wall of the fault and 2 were at the footwall. So we used the sections A and D, which are far from the fault, to estimate the regional component of tectonic uplift. And then we compared B and C, which are very close to the fault trace, to see the difference, the elevation difference, and to estimate the displacement due to the activity, the vertical displacement due to the activity of the fault. Here are the diagrams I told you before. These are at the hanging wall. These are the sections of the hanging wall, and these are the sections of the footwall. And the comparison of the 2 sections, which are very close to the fault trace, allowed us to estimate the vertical displacement due to the activity of the fault. And we found that for the period between 400 and 300,000 years ago, this rate was 0.21 millimeter per year. For the period between 300 and 200,000 years before, this rate lowered to 0.06 millimeters per year. And for the period between 200 and 100,000 years ago, this rate was 0.11 millimeter per year. And if now I can say that this rate is similar to the rate I mentioned before, due to the band that shows the Holocene activity of the Ierapetra normal fault. So, summarizing, I have to say that marine terraces are landforms that record the history of tectonics and the static sea level changes over the Quaternary. Marine terraces were used for measuring rates of tectonic uplift for the area of Neapolis, where a mean uplift rate of 0.36 plus minus 0.11 millimeters per year over the last 200,000 years was estimated, and the area is being uplifted uniformly, and the driver of tectonic uplift probably is the active subduction of the African lithosphere beneath the Eurasian plate. And the study of marine terraces allowed the estimation of the vertical movements of the Ierapetra fault over the last 400,000 years. The obtained vertical slip rates for the Ierapetra fault for the period 100 and 200,000 years is 0.11. For the period 200 to 300,000 years is 0.06. While for the last period, between 300 and 400,000 years is 0.21 millimeters per year. If you want more details for the case studies I present, you can find these papers. One of them was very, very recently published 2 weeks ago for the broader area of Neapolis. And thank you very much for your attention.
Thank you, Efthimios. Thank you very much. It was really, really interesting, and even the picture you showed us were really, really, really beautiful. Impressive was the case of the Ierapetra fault. Was really, really, really impressive. Yeah. See the active part during the Holocene was beautiful. Thank you very much.
Thank you.
So I would like to, we already have a few hands.
Can I stop sharing my screen now?
Yes,
or no?
so we can see your face.
Yeah. You see my ugly face.
I also stopped the record.
Yeah.